Wouldn't it be great if you, as a professional, can reduce your design cycle time, or you, as a teacher, can make your classes more interactive? Today, I will present various tools that will help you achieve that. Hi, I am Ankit, Applications Engineer at Wolfram, the team behind System Modeler. Today, we will see how you can reduce your design cycle time, how you can get up to speed if you are a beginner, and finally, how you can transform learning. Since the last time that we presented at the Modelica conference, we have had many improvements to help you as a user. For instance, we have added tools that make analysis of plots much faster, tools that enable you to create models using CAD data, and we have streamlined the workflows for creating control systems. Let us explore this in more detail. Model plots. Let's take the example of this series of shafts connected by clutches. Let's see the simulation results. As a user, many times you would want to do some quick analysis on your simulation plots. You'd perhaps want to find the extreme points of a plot curve or compare the plot variable between two time instants. In order to enable you to do just that, we have introduced several features. We now have a measurement window where you can record the plot data for any given time instant for your quick reference. If you are interested in comparing values between two time instants, you can do that as well. Just press Ctrl plus left click and drag to select a range. The tool provides you the values as well as difference between the time instants. Maybe there is an interesting observation that you found in the plot and want to mark it. You can do that by giving a label to it. Of course, you can position it as you see fit. Finally, you can save the measurements and labels in your model and distribute to users, colleagues, and students. CAD data. Whenever you try to use the Modelica multibody library, there are instances where you want to use your custom CAD model. However, in order to do so, you have to define all the physical properties like inertias along the different axes, center of gravity, and so on manually. This is time consuming and it may also lead to errors. Using the combination of the Wolfram language and system modeler, this process is much faster and safer. You just need to either create or import your CAD data into Mathematica. Then, using the create system model function, a multibody component with the right physical properties is automatically created. Let's use it in a new model. We will use the world component and give some initialization values. Let's simulate this. You might see an interesting behavior here. The lock nut switches. This behavior is in fact called the Janibekov effect. This effect states that for a rigid body with three unique moments of inertia, rotation about the intermediate axis is unstable, while rotation about the other two axes is stable. Control system. Finally, we have streamlined the process of creating a control system. This will drastically reduce the design time and enable you to easily use advanced control strategies relevant for your system. Let me go through an example. This example shows hovering control of a submarine. We will see how to create a controller that rejects disturbances and improves the stability of a submarine. First, we will use a model of an uncontrolled submarine. You can check the response of the uncontrolled submarine to an impulse-like disturbance. You can observe that the submarine oscillates around the equilibrium position and settles down in about 1 minute. Design a controller to dampen the oscillations of the submarine by choosing the eigenvalues of the response to be stable and well damped. The closed loop poles are placed to stabilize the system. Create a control system by automatically connecting the controller to the model in a closed loop. The submarine system is automatically connected to the controller. Check the response of the controlled submarine to the same disturbance. The controller stabilizes the submarine in about 10 seconds. So here you saw how you can create a controller and connect it automatically to your uncontrolled system and check its behavior. As a beginner or even as an advanced user, we need good resources to get up to speed. Over the past year, we have created a lot of resources that helps you get a quick grasp of the tool as well as some modeling examples to help you get started. We have added new courses on Introduction to the Modelica language, Introduction to System Modeler, and on integration between the Wolfram language and System Modeler. These are video courses with exercises to improve your understanding. Some books have been released that use System Modeler. The first book is written by professors from SMTU in Russia and University Technology Petronas in Malaysia. This book briefly discusses the main provisions of the theory of modeling. It also describes in detail the methodology for constructing models of dynamic systems using System Modeler. It provides examples from mechanics and hydraulics. The second book on Modelica is written by Abdul Hamid Ansari. This book is in Persian. Finally, we have held some study groups. These study groups are 2 to 3 weeks long event where each day we discuss on a modeling topic. This is intense but fun. We have polls and quizzes, and at the end you receive certification from us. Finally, let me introduce you to our Virtual Labs project that aims at transforming learning. According to an annual survey performed by Indiana University, 2 out of 3 high school students get bored every single day. If this is the case in high schools, then it is likely that you have encountered something similar at your college. When talking to teachers at high schools and universities around the world, we noticed that the challenges they were facing seemed to be similar, independently if they were based in Sweden, Ecuador, or Australia. Based on this experience, we started to develop something called virtual labs, teaching material driven by digital twins. Now, I will present the ideas behind them and give you a few examples. But first, let's see why the students get bored. As I said, this is an annual survey, but the results are consistent from year to year. Here you can see the key reasons according to the 2017 survey. If we look at the first one, about 8 out of 10 students don't find the material interesting. As I've heard some teachers express it, students take this class as it's required, not since it's interesting. The second one, teaching methods are not interesting. This might be extra challenging in these times with a lot of remote teaching. Gaining the attention of students during distance learning and online education is becoming critical. While the third reason relates to the first, there is a more interesting relationship between the fourth and the eighth reason. About a third of the students don't find the material challenging enough at the same time as just as many find it too difficult. This reflects something I hear teachers express every now and then. My students come with a wide diversity of skills and interests. Perhaps these challenges are something you recognize too. The virtual labs were designed with this in mind, making them easy to get started but providing challenges for the skilled students. Adaptable to current events, interactive and interesting through the use of digital twins. Let me go through these three one by one to illustrate how they relate to the challenges we have seen teachers around the world having. With students having a wide diversity of skills, depending on their background, it is important that the material is accessible to all. Exercises should be easy to get started with, independently of things like coding experience. One of the concepts that is taught in mechanical engineering is vibrations. Let's see how I was taught in college. In one of the classes, I was introduced to a model diagram as shown here. It consists of a body of mass with uppercase M attached to the ground by spring damper system. There is also a mass with lowercase m rotating inside the bigger mass with a fixed angular velocity. We were then taught how to find the vertical displacement of the body with the bigger mass. In order to solve this, we started with the free body diagrams of individual components, derived the equations, and obtained a solution. It was a lot of theory and a lot of math that made it hard to focus on the topic. We only focused on the math rather than understanding the concept and the system behavior. When a student would refer to these equations after 1 or 2 months, it will be difficult to understand. Moreover, a student can't use this material to test different scenarios on the fly, such as what will happen when I change the mass and distance of the smaller mass from the center. How would the system behave? This form of teaching is still relevant to understand the system, but this could be further improved. Let's see how we explain this in a virtual lab. We explain the same concept but using a real life example of a washing machine. You can see how it mimics the system that I showed previously. The student is introduced to the vibrations using animations. The animation shows the movement of the larger mass when the smaller mass rotates with a constant angular velocity. This really helps to understand the concept of vibration without getting sidetracked by the maths. Once a student understands the motion, he or she can test different scenarios using interactive plots. Here you can observe the movement of the washing machine for different masses of the cloths and for different damping in the machine. To make it more challenging, a more advanced student can also plot the response in the frequency domain and observe interesting phenomena like resonance. There are also various questions that will help a student to test their understanding. If an advanced student is further interested to tweak the model, he or she has full access to all the models in System Modeler. They can use it to test different configurations. For example, they can replicate the motion of a real washing machine by giving the system a ramp input rather than just giving a constant angular velocity. Let's simulate this model and check the animation. Here you see how a washing machine works in real life. It starts with a smaller mass in rest and then gradually increases speed and finally stabilizes at a constant angular velocity. A student can easily visualize the transient vibrations of the washing machine. So, here in this short demo, you saw how we focused on the concept rather than the programming and tested different scenarios without using any maths. Moreover, an advanced student has access to all the models to tweak it as per their needs, thus making the content both easy and challenging. I sometimes hear teachers saying that students take this class as it's required, not since it's interesting. This is a tricky challenge. However, exercises that are relatable to students are more likely to interest them. As we saw in the previous example, how we explained the concept of vibration using a realistic model, and we also saw that the actual models could be easily modified. Now, let us look at an example of how the Combinational Circuit Lab was adapted to solve the smart bulb problem. Let's say you have just bought a smart bulb and you have two smart switches that you want to connect to, but you have a problem. Say you have switched the bulb on using switch 1 and you want to switch it off using switch 2. You can't do that as switch 1 is in the on position. You have to rather use the switch 1 to turn it off and then turn it on using switch 2. This becomes very inconvenient. The Combinational Circuit Lab from the College Digital Electronics Library has been adapted to solve this problem. A student initially needs to define a logic that would enable him or her to switch off the bulb even if one of the switches is in the on position. They start by creating a truth table. Here, A and B are states of switch 1 and switch 2 respectively, and X is the state of the bulb. In case 1, when both the switches are off, the bulb should be off. In case 2 and 3, when either of the switches are on, the bulb should be on. And in case 4, when both the switches are on, the bulb should be off. Once a student has a truth table, the next step would be to determine the Boolean equation that satisfies the truth table. Here, the output X, which is the state of the bulb, is expressed algebraically using the Boolean representation of the inputs. Here A bar means it's a complement of A, dot means AND operation, and plus means OR operation. A student will then implement the circuit and test it in System Modeler before connecting the hardware. If the connection works fine, the student can then connect this model to real switches and LED using an Arduino. This is how the circuit should look like. Let's see how the system behaves. As you can see, as I switch on any one of the switches, the LED turns on, and as I switch on both the switches, the LED turns off. In this example, a student solves a real-life problem, tests it with a digital twin, and finally implements his logic in a hardware using Arduino. Here, we saw how an existing lab can be tweaked to adapt to a new similar event. I started by saying that a main reason for students getting bored is that they do not like the teaching methods. This is likely to be an even bigger challenge in remote teaching. So what do the students actually like? Going back to the survey, there are two key elements mentioned: discussions and technology. Thus, having material based on modern technology is likely to be more engaging. The use of digital twins is a clear example of this. Previously, you saw the digital twin of a washing machine. Similarly, a student has access to various other digital twins. In the lab on dynamics, a student can explore the working of a gimbal used for stabilizing the movement of a camera. Let's simulate the model and explore its working. We can test how a gimbal behaves by providing it a disturbance using an accelerometer connected to an Arduino. You can see how the cell phone is able to maintain a constant height despite the disturbance applied to it. This example shows how a digital twin can be used to validate and test new designs, thus saving us a lot of money and also improving our understanding of the involved mechanism. Whether it is a lab about vibrations, digital circuits, or gimbal motion, all the virtual labs are based on digital twins and use cutting edge technology to drive discussion and learning. We currently have about 100 weekly downloads of these virtual labs, and we have 6 libraries in our library store. Many more libraries are also in the pipeline, planned to be released soon. Existing ways of teaching using only presentations and Blackboard have no doubt worked for a long time. We believe that this teaching approach is still required to get a full preliminary understanding of the physical systems. Using virtual labs, this approach can be assisted by the real-time simulation of the systems to get a fast hands-on experience on their actual operating conditions. Moreover, creating these virtual labs require no prior knowledge of low-level coding, which is a plus for students or teachers without a solid programming background. To summarize, we have tried to develop the virtual labs with 3 key values in mind: easy and challenging, adaptable to current events, and use of modern technology. Let's look what students have to say about it. Here is Ulrika from Sweden, who was studying logistics and optimization. She was involved in creating the high school chemistry labs. Even if she is not directly related to the engineering domain, she got to know about different topics on mechanics and electrical engineering just by browsing through the virtual labs. Anna was studying applied mechanics in Australia. She has been involved in the creating the high school biology labs. Interestingly, she found System Modeler especially useful for students who lack mathematical background. Finally, we have Julius from Peru who was studying control designs. He liked how the Wolfram technologies could automate and save his controller development time. Before I wrap up, let me share a story of Professor Matteo from Politecnico di Torino in Italy, who helped us develop the college thermal library. He wanted to transform the way he was handling his classes by introducing model-based learning to his students. He wanted to have the virtual labs in a computer lab with a capacity for 30 students. But with the unfortunate COVID-19 situation, he was unable to do so as the colleges were closed and students were forced for remote learning. However, Matteo decided to share these labs with everyone using the system model library store and introduced it to his class of 300 students. Each student has now access to these labs. It is interesting to see that Professor Matteo was able to solve a problem which didn't even exist before the pandemic. If you are a teacher and you want your students to experience innovative learning processes, take an extra step to transform your courses with the help of flexible, intuitive, and high-level programming of the Wolfram language and its modeling environments. If you have any ideas or questions on how you could improve your teaching capacities, do contact us at virtuallabs@wolfram.com. Now let's open the floor for Q&A.